plan for this lecture and the next lecture is to talk about more advanced algorithms and other algorithms that you may not have seen so far. Right? That is the plan. And so towards that, I wanted to maybe have one lecture where I would do more maybe numerical algorithms, things like the fast Fourier transform, maybe like Gaussian elimination, talking about some of those things, maybe gradient descent, obviously at a high level. So today what I'll do is I will talk about an algorithm or a problem that's officially on the syllabus, and that is the problem of min cut and max flow. But again, as I said, today's lecture will be somewhat again lower on mathematical detail, higher on the ideas, because I want to give you an idea of what these problems are and how they're related to various questions that we have. So a lot of this discussion really begins from the fundamental problem of what is called graph partitioning. So what is graph partitioning? So I have a large graph G. Let us for now assume that it's simple, maybe not even simple. We'll just assume it's undirected. Right? So it might have weights on it. And what you want to do in graph partitioning is usually break it into two parts. So you want to find what's called a cut. And so this partition SS complement is a cut. Right? So you want to break the graph into two parts, and often the weight of the cut is equal to the summation of U in S, V in S complement of the weight of UV. Right? So typical what you might expect, right? Nothing surprising over there. This is called the weight of the cut. And now what you have is you have a whole series of problems you can ask regarding this. So firstly, maybe it's worth asking why you would want to cut your graph. So where does this occur? So initially, at least, one of the places where it occurred was parallel algorithms for solving linear systems, which is linear systems of equations. Okay, so just to motivate how things like that came up, well, the idea is when you want to solve a linear system, you have some kind of matrix. A, X is equal to B, so you have X is over here. Right, you're trying to solve for X, and you have some matrix here. In some situations, this matrix would actually be symmetric. You could imagine situations. And suppose A is sparse, means that there are few non-zeros. So the idea is that you could basically, G could be the adjacency matrix. Right, G is an adjacency matrix. If G, let's say A is sparse and symmetric. Like in general, A might not even be square. But in many situations, you actually come up with A that is symmetric and sparse. So A is a square matrix. Situations that happen like this are, if you actually go back to a lot of work in the 50s and 60s, a lot of it was on essentially what's called simulating a physical system. So when you simulate a physical system, it's like you want to do climate simulations, for example. Now, how do you think people actually do climate simulations? Do you have any idea? Now, how do they predict the weather? I mean, somebody's doing it. So what they do is they say, well, look, so if you think about physics, every particle, you might say, has every coordinate in the world has a temperature, has a pressure, has a humidity, right? So you set that. And then you say, okay, according to the laws of physics, this will evolve. So the temperature at a place will become the average of its neighboring temperatures. The humidity might do something. Maybe there's wind. So you kind of put all of those things together. But if you look at the update at every step, the update is usually a linear update. It's like average your neighbors. So this is also, so what it gives is a large linear system that you keep evolving over time. And it's kind of symmetric because what you have is, you think of each of this as like one grid point in space or on land. And the neighbors are the neighboring grid points. This is called a finite mesh. And then you just solve this linear system. The system is sparse often. So what you do is you take the graph, and if you think about what these things are like neighboring particles that affect each other. So the pressure over here is going to affect the pressure over there. But if you look at an edge here, the update over here does not affect the update over there. So you could try to solve these portions independently and combine the solutions. Now, what you want to do is minimize the number of things that are cut, because that's where you get errors. Right? Because when you do an update at this vertex, ignoring this vertex, then you have a problem. So you have some error that comes from the cut. And then you have to figure out how to patch that error. And there are ways of doing this. So you basically break up the linear system using a cut. And the cut should have small value. Right? So that's where you want to maybe minimize the weight of the cut. So it's common to say find the minimum weight of a cut. Does that make sense? But this is one version of this problem. The problem with just minimizing the overall weight of the cut is maybe there's just this one vertex hanging out over here, and that is the min cut. That is the minimum cut. That could happen. So sometimes you want to say, no, I want you to break it into two parts that are roughly the same size. Right? So then you could do a variant. It's called min bisection. So you enforce that S should be equal to S complement. Or maybe roughly, you could say, well, min bisection, you could do like, balanced cut, which is to enforce maybe that S and this should be at least alpha times n. Alpha is some constant. So an alpha is a half that's it's basically min bisection, but you might say it's okay to get a 1/3, 2/3 split. So there are lots of variants of this. Another common variance, it's what's called conductance. So there are many possible ways of defining conductance. I'm going to give you one of them. One is you could say, okay, so this is technically not conductance, but it's similar to it. You could say the weight of the cut divided by the smaller size of the smaller portion. So what you want to do is you want to normalize by how many things you're cutting out. So what you want is you want this to be small and this to be large. You want to divide it into roughly even pieces, but you kind of normalize a different way. Does that make sense? Questions?
If you're maximizing that?
Minimizing. You're minimizing all of this. You're minimizing these quantities. In all of the discussions today, we're trying to minimize because we're trying to sort of break it into two parts that are each internally connected well. Okay, so that's another problem, min conductance. And so there are many variants of cuts. Another place where this happens, and this happens, well, so far so good. So I want to relate this to something else. I'm going to talk about something that is seemingly different, and it turns out to be closely related to cuts. So that was the problem of cuts. Now let's look at the problem of what's called diffusions and flows. So maybe the easiest way to think about this is you start with a graph. Now this graph, let's say, may even be directed. Okay. In general, what I said previously really doesn't, conductance uses undirected, but many of the others really, you could do it for directed systems as well. There's nothing about undirection that's fundamental to these definitions. So you could just consider the following process. Start at S, randomly walk to a neighbor, and keep repeating this process. So I start at a vertex, I go somewhere, and I go somewhere. Maybe using the direction, I go to a random neighbor. Maybe this is weighted. Depending on the weights, you could kind of. So if you think about what this is doing, it's like a process, like a person walking through the graph. You could say, where does this end up? A different way to look at this is called diffusion. Start with 1 unit of ink at S, and the ink spreads to the neighbors proportional to weight. All right, and this could keep repeating this process. And this process is called diffusion. Now, I'm willing to bet that if not today, then at least yesterday, you have actually used an algorithm which uses diffusion. How many of you have done a Google search in the past one day? How does Google do its searches? Have you heard of something called PageRank? You might have. PageRank is doing diffusion. So what it says, I'm oversimplifying, but PageRank says that diffusion leads to important vertices. That was their point. If you diffuse from somewhere, many different places, and you keep ending up at the same vertex over and over again, that's an important vertex. So the concept of PageRank is diffusion from random starting points, random starting vertices. Or I'd say if diffusion from random starting vertices ends up at the same vertex, V, then V is important. Okay? So the idea is that instead of, now you might say, how does this link to search? Well, so let's say you're searching for a particular keyword. And what Google has done is indexed the text of various websites by the word they have. And so you search for shoes, they'll look at a bunch of websites that involve shoes, start diffusion from there. And all of those things maybe end up at Nike and Reebok. And then you say, okay, maybe let's rank these. This is not the only signal that they use, but this is one of the initial signals they used when initially Google was built. And it was this notion that diffusion tells you which vertices are important. Yeah, question? Okay. So, all right, so why am I talking about diffusion and flows? So it turns out there's a deep connection between cuts and flows. So if you think about it, look at diffusion. And let's say diffusion from somewhere is stuck, meaning that the ink goes there and the ink is just not spreading. Why is it not spreading? It's not spreading because the cut is small, in some sense. Right? The reason why diffusion doesn't spread is because the cut is small. Or it has bumped into a small cut. This is, of course, very hand-wavy. I'll make this more precise. It's stuck because this is a small cut. So this notion of diffusion getting stuck at small cuts is one of the key ideas that links cuts and flows together. Conversely, if there are no small cuts, things will diffuse easily. Okay, this is sort of there's a deep concept called duality that relates these things. And this comes up in many, many different contexts where a cut and a flow is the same thing. So initially, these look like two very different problems. One is to cut, the other is to understand diffusion. And yet they're related. So one way in which this is actually done, again, in practice, is let's just say that if you look at your common social networks, how do they recommend who you should follow or what content is relevant for you? There's some way in which they're deciding, here are the things that you should be looking at. Now, if you think about it, there's just so much content out there. What signals are they using to decide that? Again, there are many different signals, but one of them actually is related to cuts and diffusion, which is I diffuse from things I know you're interested in. I kind of look at where the diffusion ends up and say, okay, those are the things that should be recommended. And so there are many ways in which you can set this problem up. Conversely, wherever the diffusion gets stuck is a cut. And if I look at that cut, then I start finding people who are similar to you. That's why a lot of your behavior on social networks leads to very precise, maybe in a good way or a bad way, maybe in many ways a bad way, but it leads to very precise characterizations of what you're interested in because the diffusions will immediately pull that information out. Even though your neighbors, so just by looking at your neighbors, and kind of weighting things appropriately, one gets a lot of information. You can look at this as a good thing or a bad thing, but I don't care. It's just the math. But still, yeah.
What does it mean when a diffusion gets stuck?
So what it means, okay, so how does one formally defines that is to say that. So think about it as, suppose you were to think about it visually as color, right? So you put ink. So initially the ink is very dark because it's one unit of ink that's stuck on one vertex. Eventually that one unit is spread over many vertices. So if you track over how many vertices it is spread, and you kind of plot that as a function of time, initially it's probably like the average ink on a vertex is decreasing. Right? And at some point, that average doesn't decrease anymore. Then the ink is kind of stuck. I don't know if that analogy makes sense. You can make it formal by looking at various mathematical quantities on that. Another way to look at it is you could say, it's equivalent to saying, if I randomly start here, what's the probability I end up somewhere? This is the region of high probability. And this is the region of low probability. So high probability versus low probability is like getting stuck. Yeah?
So if you were to start from outside the cut, would it go inside the smaller cut?
It depends. It could, depending on how the connections are. Anything could happen. So again, there are many different variants of this question. Here, usually what you're trying to do is try to understand what is a cut around a vertex. So you have a starting point that you're actually interested in. Yeah?
Eventually, if you just wait forever, then all the vertices will have, or everything.
Exactly.
Will have. So
Yeah.
How do you know when to
So there is, yeah. So you have to, there's a whole math behind what this is. So you're right that as t goes to infinity, as time goes to infinity, the ink is everywhere. So what you instead do is some sort of rate of change, and when that rate gets stuck somewhere or it changes, if the rate is initially so by rate you could say, what is the average amount of okay, so formally you look at something like the 2 norm, So you could look at how much ink is on each vertex and look at the Euclidean norm of that as a vector. And you look at the length of that. So actually, in the limit, the length of that, the length always decreases. But the rate of change tells you when something interesting is happening. So if at some point that length does not decrease enough, then at that point you say you should cut. So that's usually how one does it. Okay, so another interesting thing that happens in this is it connects two things. The combinatorial view. The combinatorial view here is cuts and like the discrete graph perspective. By combinatorial, what I mean is things that only involve like discrete objects, not continuous numbers. So when I give you this problem, as stated, it looks very much like our NP problems, the NP optimization. Right? You have an exponential many choices over here, you're minimizing over it. So it looks very similar to the kinds of things that we did in the course so far. This picture seems like a lot more of a continuous viewpoint. So the continuous view, I'd say, is sort of the continuous view is really diffusion and linear systems, sort of like ink norms. I mean, I'm using ink sort of in the language that we're using, but technically you look at you look like distribution norms. This is for those who may have heard some of these terms, not ink, but the diffusion norms. So there is some sort of relationship between this view, and this leads to lots of beautiful math, but lots of very interesting algorithms to solve fairly challenging problems. Okay, so with this sort of long introduction, and sort of the point for me to give you this introduction is to kind of maybe tell you how these ideas actually impact things that are being done today. Like contemporary algorithms use a lot of these concepts. Things like PageRank, things like partitioning a social network, graph partitioning. So you could imagine that you also use this to partition a large graph to store it, because you want to break it up into parts where there are a few edges between, so that you can do local computations quickly. And so a lot of contemporary parallel algorithms will also be looking at partitioning a graph. Okay, so with that, let's talk a little bit about the problem of maxflow. Okay, so what is maxflow? So we start with our graph. This weighted, directed doesn't matter. Okay, it's weighted. Think of it as just weighted and directed. Weighted and directed. Okay. Now, for convenience, I'm going to refer to the weight using C. I'm going to say, and these are non-negative weights. So C, I'll call it C of UV is whatever, something. Okay, I'm going to call it C, not W. And that's because C is going to refer to capacity. Okay, it's going to refer to capacity. And we have a source, vertex S, and a destination, vertex T. Okay, so there's S and T. And so the story that you have here is you are trying to send flow from S to T. You can even think of the flow as just like whatever, it's water or some commodity. So you're sending S units of flow from S. You want to send unit flow from S to T. Each edge has a capacity of how much flow can be sent. So the capacity is the maximum allowed flow on the edge UV. So if you have UV, and note that there may be different capacities from U to V and from V to U. That's okay. Okay, so that's the amount of flow that can go through that single edge. And now you're routing flow through the system, so you have to route flow. So the question is, what is the maximum flow that can be routed from S to T? Does the question make sense? And another way of looking at it, flow goes along paths from S to T. Okay? So flow goes along paths from S to T. So another way of looking at this is, one analogy given is you could think of actual commodity like trucks that have to be sent from S to T. Each road can only take so many trucks. How many trucks can you send from S to T? Obviously, they'll try to take many different paths. And you're looking at the maximum flow that goes. There are many variants of this problem where you can even like start having prices on an edge. Well, say for each truck, I have to pay some price. So if I can only pay this much price, then what is the maximum flow? Like there are many different variants and add-ons to this problem. Okay, any questions about this? Okay. So this is the problem of max flow. So you're given a graph with the capacities, you're given a source and a destination, and you have to compute how much flow goes through the system. Okay? So what is not at all obvious, but very interesting, is that there is a polynomial time algorithm to solve max flow. But and I'm not going to go through a polynomial time algorithm. I'm actually going to probably tell you Ford-Fulkerson, which is not polynomial time. But what is really even more remarkable or fundamental fact is something called the maxflow min-cut theorem. So we talked about the problem of max flow. Now let me tell you about a different problem, and we'll see that the solutions are related, and indeed actually they will be the same. Okay, so instead let me tell you about something called the ST cut. So an ST cut is a set S. S contains little s, and S complement contains little t. So what you want to do is you want to break up the graph into two parts, one part containing S, the other part containing T, and minimize the capacity of UV, where U is an S and V is an S complement. So this is like the min-cut problem, except, okay, you're looking at direction here, but you could also make it undirected if you wanted. Right? If you make it undirected, then essentially every edge just gets, one capacity. You could imagine that every edge, undirected edge, is like two directed edges, one going forward, one going backward, each with the same capacity. Make sense? Okay, so this is the ST cut, and this is referred to as the min ST cut problem. In general, the problem of min cut would be to just minimize where both, so when you have this condition that you want to separate S and T, it's the ST cut problem. If you have no condition, you just want to cut it into two parts, and you don't care about the sizes, that's called just the min cut problem. Okay? Okay, so let's look at this problem and try to understand how these problems relate to each other. Yeah, question?
Do you minimize the summation?
I'm sorry, yes, sorry, minimize. Sorry. It's the min overall S of this summation. Minimize over that summation. Sorry about that, right? Over here? No, you're not minimizing over S and T. You're minimizing over all S that satisfy this condition. It's the ST cut, right? You're given S and T. You're minimizing over all S that satisfy this condition. In the min ST cut problem, you want to separate S from T. In general, you just want to cut it into two non-trivial, non-zero parts. Okay, any questions about this? Hopefully I haven't said anything particularly complicated thus far, but now let's start doing some math. How do you relate the ST flow problem to the ST cut problem? Suppose the min cut value is really small. What does that tell you about the flow? So I'm going to draw this as a separate picture, and then maybe you'll start seeing what's going on. So here's ST cut versus ST flow. So here's S, here's T, and this is some cut. Some cut, doesn't matter, it's some cut. What can you say about the flow given the value of this cut? Does the question make sense? Can you send more flow than this cut value? No. Because if you think about it, like the flow, any flow that goes from S to T so think of these as like bridges in between. And no matter how you go from S to T, you have to take one of these bridges. So the total capacity of these bridges is the total amount of flow that you can. It's an upper bound. It's an upper bound, right? So what this says is, so the claim is, for all S that contain S complement containing T. So let me just define the cut value of S to be equal to this quantity. U in S, V in S complement of the capacity of UV. I'm just going to call it the cut of S. So for all S to T, the flow, the ST flow, is at most the cut value of S. Okay, instead of me writing a formal proof, it's just more important that you see the picture here, right? Because all the flow that goes from S to T has to cross the cut at some point. At some point, think of a truck that's going, it has to go from S to T. It has to leave S and enter S complement. And so the total capacity of the cut, this is also called the capacity. So maybe instead of cut, let me call it the capacity. Okay? Call it the capacity because it's, sorry for the mess. That's the capacity of the cut. Okay, so note that this holds for all. The min cut, the min ST cut, is just the minimum over all S containing S, S complement containing T of the capacity of S. Right? That's what the min cut is. So clearly you have this claim that the max ST flow is at most the min ST cut. You cannot send more flow than the min cut. And this is sort of going back to our pictures with diffusion and cuts. It says that the cuts impose a constraint on how much flow can go through the system. And this connection comes up in many different ways. Like even when so of course the kinds of diffusion I talked about here where 1 unit of ink is spreading is different from you having to send many trucks. Right? And the math does tend to be different, but this principle in general manifests in many ways. That there's this relationship between this. Does this make sense? The max ST flow is at most the min ST cut. But this was proven first by Ford and I think Fulkerson, I forget, maybe 60s or 70s. My dates are getting messed up. Maybe it's the 60s or 70s. I forget exactly when. And they said actually the max ST flow is equal to the min ST cut. And this is known as the max flow min cut theorem. So this is sort of remarkable because it says that this is only giving an upper bound. There's no reason why you should be able to send that much flow. But the max flow min cut theorem says you can actually send the min cut. And for those of you who've heard it, this is also related to LP duality. Actually, indeed, it is a special case of LP duality, which I will talk a little bit about linear programs at some point. So does the statement of the theorem make sense? So what's now really neat is, I mean, okay, this isn't obvious given what I've written here, but if you can, at least if you can compute the max flow value, then you know the min cut value. And as it turns out, if you can compute the max flow, you can actually even find the min cut. So actually, min ST cut is in polynomial time. Min cut is also in polynomial time, which is again not a very obvious theorem to see. Despite it looking like something that is probably NP hard or NP complete, it's actually in P. On the other hand, a lot of these other problems that I said, like min bisection, balance cut conductance, these are hard. Yeah.
When we are talking about flow, we are sending from one source to one destination.
Correct.
But when we are talking about cut, we are separating two sets of vertices.
No, just two vertices.
Two vertices.
You're just separating two vertices. You are not separating two sets. You're just separating two vertices. Your S and T, you're taking some set that contains S such that its complement contains T. This is a partition, right? S and S complement is a partition. So you're partitioning into two parts. One part has S, the other part has T. Okay? Does that make sense? Okay. So let me give you But, okay, so I will give you an algorithm to solve flows, which is the someone else. Can you find the max flow if you have the min cut? Again, it's not obvious that you can. Just given the min cut, I don't think even given the max flow, it's kind of not obvious how you would find the min cut. What I'm saying is that the algorithm itself will implicitly find it. But it's not obvious how to compute one given the other, even though you have this equality. Okay, let me give you a very nice, actually forget it. Let me first give you the Ford-Fulkerson algorithm, and then we can talk about other things. The Ford-Fulkerson algorithm is not a polynomial time algorithm, but the ideas behind it are some of the most key ideas when you want to understand max flow min cut, or just understanding min cut. I don't even know if I'm going to prove this theorem explicitly, but we'll see that the analysis of Ford-Fulkerson kind of gives you the proof. Okay, so let's do the side, and let's talk about the Ford-Fulkerson algorithm. Okay, so the Ford-Fulkerson algorithm, there are many ways of looking at this. One way that I would like to present to you is it's kind of like it's some kind of a gradient descent, or like a greedy algorithm. So the idea is suppose we have already sent some flow represented by a vector or a function f. So what this means is, just like you have capacities fu, so you could think of f uv is the flow sent in the edge uv. That's the amount of flow that you've sent so far. Your aim is really to compute the optimal values of this quantity. So let's now write down, okay, so the Ford-Fulkerson algorithm is going to require some amount of background, so let me go over that background. So FUV is the flow sent in that edge. Okay, so you're sending some flow. What you know is that for all UV, f of UV is at most the capacity, because that's what it means to be a flow. You're not allowed to send more flow than the capacity. Okay? So this is known as the capacity constraint. What we also have is for all V not equal to S or T. Okay, so now I'm going a little bit into what does it actually mean to have a flow. If you think about what it means is, if you look at any intermediate vertex V, the amount of flow that goes in has to come out. Right? Because it's like the trucks can only start at S and stop at T. But at any intermediate vertex, they have to go through. So there's some kind of conservation. The amount of flow that comes in is equal to the amount of flow that goes out. For every vertex that's not S or T. S is going to be sending flow, T is going to be receiving flow. But every other vertex is like a conduit, where the amount of flow going in is the amount of flow going out. So what you have over here is that, I'll write this as F. Okay, so Okay, let me write this in a particular way, and then we can discuss later on. So this is f over all vertices u. This is like the flow going in V, right? Because I'm summing from all vertices into V is equal to the sum for all vertices of f VU, which is the flow that goes from V to that vertex. What's most probably happening is that in general, you'll never have a situation where a vertex sends flow to some neighbor and the neighbor sends it back, because there's no point in sending flow back. This is equal to the flow going out of V. So this is called conservation constraint. So what do I mean by a flow? I mean any f, non-zero f really, any non-zero f that satisfies these constraints is a flow. So now we're being a little bit more formal of what it means to be a flow. It just means a set of numbers, non-negative numbers, so that each is at most the capacity and they're conserved. Okay? So suppose we have some flow. The question that Ford-Fulkerson, the algorithm, asks is, well, okay, can you send more? Is there a way of incrementally sending some more flow? Okay? Is the question clear? Yes, no? Okay, so so the key construct of the Ford-Fulkerson algorithm is something called the residual graph. So residual graph is given a flow f, gf is the residual graph. So the way to think about it is gf has updated capacities. So it's kind of like saying that if you have an edge uv, okay, let's just say that initially, let's just assume that capacities were only in one direction, just to keep things simple. Right? So initially, for every edge, you can only send flow from u to v or v to u, not both. Okay, just let's keep it simple. So initially, you had a capacity of C uv. Now suppose you sent FUV flow through it already. How much flow do you have left to send? What happens to the capacity of that? How much capacity is left? How much capacity is left? So you have CUV. Just subtract FUV. That's how much capacity is left. But now this was the genius. It says that actually in your next iteration you could try to reduce the flow on that edge. You're already sending FUV units of flow. Maybe you want to reduce that flow to send it somewhere else. You can model that by instead putting an edge from here whose capacity is actually FUV. That's like saying that you are also now allowed to send FUV units of flow from V to U, which kind of cancels out the flow that you had initially. It's a remarkable trick. I mean, actually, the more you think about it, the more you'll be amazed at it. So the first step is kind of obvious. Because you're saying, well, you sent FUV units of flow from U to V, so obviously you reduce. But the opposite, which says, actually, if you put a back edge, and you're actually now allowed to send FUV units of flow from V to U. Because what that would mean is it would really cancel out the flow that you were sending. Okay? It's basically a syntactic operation on the graph now. So you can, given a graph, you can compute G of F. It's just linear time computation. Right? It's an O of M computation. So in O of M time, we can compute G of F. Right, given F, given F, we can compute G of F. Okay? So now let's just say you have G of F. And you have S and T. So you have this new graph. Find any directed path from S to T. Just find a directed path. Then you could send flow on this path. Right? Because each edge has some non-zero capacity, because all of these are non-zero. And so if you find a path, you can go ahead and send flow. And if you can send flow, then you've improved your flow. So the Ford-Fulkerson algorithm just says, it's, of course, you initialize F to be all 0. Right? All the flow is 0. Then it says, while S is connected to T in G of F, route flow in a path from S to T update F and G of F. That's the algorithm. That's it. It just says, well, if it's connected, which means there is a path, so this you can do step 2, that you can do with the BFS. You can do it with a single BFS. Right? Because you compute the residual, then that's just a BFS to find a path. And so it just keeps adding flow. This is known as augmenting, well, rather, that is called the augmenting path. The augmenting path is, once you compute the residual, it is the path that goes from S to T. It's called an augmenting path. So you augment on that path, you recompute the flow, so on and so forth. Okay, is that clear? So this is the augmenting flow, or Ford-Fulkerson. It's also called the augmenting flow algorithm. So there are two questions here, of course, is why is this correct? So what you can do is we can prove that as long as the current flow is less than the min ST cut, as long as the current flow F is less than the min ST cut, S is connected to T in G of F. So we can prove that. So as long as your flow is less than the min cut value, it turns out you can prove that S will be connected to T in the residual. Conversely, when S is not connected to T in the residual, you must be sending at least the min cut. But you cannot send more than the min cut. Hence, your flow is basically optimal. This actually proves the max flow min cut theorem, if you follow this. Okay? So what you do is, hence, when the algorithm terminates, the flow value is at least the min ST cut. But it's actually equal to this. Actually, it's equal and hence optimal. And the proof of this statement is not very difficult. Like if you look at the residual flow graph, you can kind of make this argument. Okay? Question? Yeah.
So when the residual of an A becomes 0, it disconnects.
So yeah, I mean, if you essentially route the entire flow through it, like if you route CUV units of flow, the edge becomes empty, but then the back edge will now start having a capacity. So in some sense, there's a trade-off. Like the sum of capacities is always CUV. So you never actually remove, you never remove both sides of the edge, both directions. One of the directions is always alive. But what eventually happens is, if all of them are pointing towards S, then S can never get to T. So that's kind of what's going on, right? At some point, all the edges will sort of point backwards. And so you cannot route flow from S to T. And that's basically the algorithm. This is the Ford-Fulkerson algorithm.
So why do we need the back edges? Like even if there was no back edges, if we kept subtracting, wouldn't there not be a path from S?
No, so then actually things can go wrong. So let me try to give you an example of, because what could happen is maybe there is still a way of going like this and going like that. Okay, so let me try to draw an example. Usually the simplest examples start with this diamond sort of construction. Let me see if I can. Okay, so suppose you did the following. Let's say all these capacities are 1, so you can send 2 units of flow. And I'm also just going to put this 1 unit capacity bridge. You don't really need it in the optimal solution. But still, maybe the first time you decided to route like S to U, U to V, and V to T, because you could have done that. So once you do that, what's going to happen is that if you did what you were suggesting, just removing the edges, you would remove this edge, this edge, this edge, and you'd be stuck. You wouldn't be able to route that one more unit of flow. But actually what happens is if you put the back edges, you would then route from S to V to U to 1. And if you kind of overlaid those paths on each other, you would cancel out the flow in the middle. So it's almost like it's allowing you to send negative flow to correct any mistakes that you made. Think of it as if you went from S to U to V to T, that's like you shouldn't have done that. But how does your algorithm know locally that you're not supposed to make this decision? So the back edge gives you the chance to correct for that mistake. I don't know if that answers your question. So of course, this was a very simplistic. You could imagine some structure like this in a bigger graph, where at some point the algorithm doesn't know which way to go. Right? So what happened here is that the algorithm in its first choice made the wrong move. Because from U, it decided to go to V instead of T directly. Like I could come up with like other things over there where it would look like going to V is the most natural thing to do. Because maybe this is much closer and that's a much longer path. So it decides to go quickly this way. Does that make sense? So you could imagine that maybe there were lots of vertices in here. And so the algorithm decided this is too long a path, let me go on the shortest path. So it takes a short path to get there. But then actually the second thing will then correct. The back edge is allowed to correct incorrect decisions. Okay, so that's the Ford-Fulkerson algorithm. Any questions about this? I mean, I haven't given you any proofs, but. So what is the running time of this? Let's assume that all the capacities are integers, positive integers. Okay. How long does a single iteration take? Just one iteration.
Like linear time in the graph?
Linear time in the graph, right? It's just because there's a BFS, and then there's the update, which would be linear time, right? So one iteration runs in basically O of m plus n, right? Linear time, which I'll just say is O of m, right? Because I'm assuming m is at least n. The number of iterations is at most the total flow, because every iteration increases the flow by 1. Because they're all, assuming capacities are all integers, every time I route at least 1 unit of flow. Right? Because all of these are integers. So whenever it's non-zero, it's at least 1. So the total running time is often written as O of mf, where mf is actually the final flow value. This is not a polynomial time algorithm, because f is really like, think about it as f is really exponentially large in the size of the representation of the bits of the capacities. So technically, this would be called pseudo-polynomial. Because it depends on, it's like, think of it when you do minimum spanning trees, there's no dependence on the actual weights. It only depends on the size of the graph. Same with Dijkstra. This is kind of weird because it actually depends on the weights. And you can show that actually this is tight. You can construct examples where actually it will take that much time. And they look a lot like my diamond example, where you kind of make an incorrect move each time. And so you keep just adding 1 unit of flow in each go. Okay, so there are polynomial time algorithms. The study of max flows is a hugely influential topic in contemporary theoretical computer science. people have a variety of practical and theoretical algorithms for this problem. But this is sort of the Ford-Fulkerson, this is sort of the basic story. Okay? Let me give you an example of a problem. No, actually, okay, so we have about 20 minutes. So let's take a break for maybe a few minutes. So you can breathe, I can breathe. It's actually, it is gradient descent actually. In the space of flows, this is actually a gradient move.
Okay.
And so in that sense, it's kind of greedy because it just makes local improvements to its position. If you think of gradient descent as a greedy algorithm, there is actually a formal way of interpreting Ford-Fulkerson as doing gradient descent, which is actually the magic of, like, it basically takes this continuous viewpoint and puts it in this discrete perspective.
Are there other, like, greedy algorithms that have, like, the possibility of unmaking choices you made in the past?
Well, I don't know. I don't have good examples at the top of my head. I mean, I guess that's the amazing thing here, right? It's a greedy algorithm that actually fixes its choices. It's a good question. I don't know of anything compelling. Let's see if this actually goes on all the way. See if this works. Okay, there it is. All right, so we will. For once, I'm actually going to do slides, but this is more like this is more fun rather than anything mathematical. But okay, and this is going to be related to what we just did. But okay, so any questions about Ford-Fulkerson? So before I actually want to. We switch back to the document camera for a second. And go back to this. So what is the flow? It's just a variable. For each edge, you want to construct this. Think of it as a variable, FUV, which satisfies these constraints. First is capacity. It's non-negative. It's at most the capacity. The sum of flow going into a vertex is equal to the sum of flow going out. Any set of values f that satisfies these constraints is a valid flow. And what are you trying to do? You're trying to maximize the amount of flow leaving S. So you could think of it as what you're really trying to do is optimize the max of the sum of f SU. Like that's the amount of flow that's going out of S. And you can argue that that's the amount of flow that will come into T, because everywhere else it's conserved. So, okay, so let's keep this in mind for a short bit. And let me now tell you something completely different. It's surprisingly, different, yet sadly enough relevant to what's happening today in the world. But hopefully this should start. Okay, there you go. Okay, so what is the history lesson? Again, the history lesson, I don't know, it's somewhat shockingly relevant to what's happening these days. So anyway, this is a picture of Europe right after World War II. Okay, and does anyone know what is the outline of that? What is that outline? That's Germany, right? And so there were essentially, the Allies were effectively primarily 4 countries in the Allies: the Soviet Union, England, the United States, and France. And so what they did was they had essentially divided Germany into 4 parts, each controlling one part. What was surprising is if Berlin is this island inside the Soviet part. And Berlin was itself divided into 4 parts. Right? So Berlin is deep inside. I mean, for those of you who remember, I guess this is before your time, but it was definitely in my time, that there was East Berlin and West Berlin. And so this picture over here is West Berlin, and that red part is East Berlin. So this is how they had divided right after World War II. So in 1948, what the Soviet Union said is, we are not going to allow any road traffic into Berlin. Because they said, they were allies, but they were sort of frenemies, as is still going on. And so they prevented any Allied traffic into Berlin. So this is 1948. And so Allied Berlin, which is the portion which is not in red in Berlin, had basically 36 days of food and 45 days of coal. And winter was coming. So what the Allies decided to do was, the point was, I think, apparently what Stalin had hoped for is, because it's just infeasible to actually keep West Berlin alive, they would essentially give it up, and then that would just be all of East Germany. So his hope was that Berlin would become part of East Germany, but the Allies had, let's say, a very strong political reason to keep Berlin. And so what they needed to do, what they decided was to airlift. So if you look at the map up there, they said, because there was nothing about air traffic, it was only road traffic. So they said from the Allied part, they would airlift supplies into Berlin. And if you look at it, this is what I could find online. The daily supplies required were like 646 tons of flour and wheat, 125 tons of cereal, 64 tons of fat. There was a whole list of what they had. And then they had planes. And each plane could carry 3.5 tons, and it could do 100 round trips per day. So this was the problem that they had. So the question is, how do you optimize this? You have some constraints, which is how much supplies have to go in. And then you have some constraints on how much you can send. I'm sorry, actually, what I should say is you have a demand. This is a demand. This is what you need to do. And these are the constraints. So it looks like flow if you think about it. Flow basically says you had constraints that were given by the capacities, and then you just wanted to maximize how much you can send. But here you have multiple commodities, and you wanted to send. And so it's essentially a resource allocation problem. And this comes up a lot in any kind of optimization setting where, like, these are things like said, okay, the cargo capacity is this much cubic feet for an American plane. You could use at most that many planes per day. The total number of personnel was so much. The cost was this much. How do you maximize how much you can airlift, given maybe some demands on how much cost you have? Right? The total weekly cost could not exceed some limit. So there are all these constraints that were given. When you write down all those constraints, it actually looks a lot like maxflow. You would have linear constraints. These are all linear constraints. What's important to note is that if you think of your variables as, what is your variable? How much wheat can I put on this flight? That's a variable. So you write down all these variables. And then you have linear constraints. The total amount of supplies on any plane is at most this much. The number of planes I have is this much. The total amount of wheat I need to send is at least this much, so on and so forth. And from that actually supposedly came the simplex algorithm, which is to solve linear programming, which is maximize linear objectives with linear constraints. Since the earliest documented use was in the Berlin airlift, where, I don't know, Danzig is over here, who came up with the algorithm that I will probably talk about in the next 20 minutes or 15 minutes because it's related to maxflow. And this is a very common algorithm used in logistics planning. It was preceded by Kantorovich in 1939, who also defined linear programming. So the story, of course, is that the blockade lasted for 1 year, but the airlift was successful. So they actually were able to keep West Berlin alive. And then, of course, the rest is history. That's the fall of the Berlin Wall. So this is like math helping history at some level. But so why am I telling you about the Berlin airlift? Because if you go back to this problem here of max flow, it has this similar feeling where you have certain variables. Your flow is like the commodity. Capacity is how much can go into a flight. And then this was a linear constraint. So actually what turns out is that max flow as a special case of a more fundamental problem called linear programming. So what is linear programming? Linear programming, think of it as we have variables x1 to xn. We usually have some kind of objective, which is to say maximize some summation of ci xi, I going from 1 to n. These are some constants. That's the objective, and then you have constraints. So all of these are going to be linear. So the constraints would be, something that says summation of I going from 1 to n of, I'll call it alpha ij xi is at most b of j. So for j going from 1 to m. So think of there being j constraints. For each j, I have a different constraint, and these are all constants. Max flow is essentially of this kind, except here in max flow is an equality constraint. But in general, I allow inequalities. In max flow, actually, there is no bj. It's just that some of the alpha ij's are 1 and some are minus 1. Because it's like some sum is equal to some other sum. But if you move it all to one side, you have plus 1s, minus 1s. You had a constraint. The capacity constraint was where this b was actually this capacity. The objective was just the amount of flow going outside of one vertex. But everything is linear. Right? Everything is linear. And this is also known as an LP, if you've ever heard of it. This is one of the most fundamental optimization problems that comes up. And indeed, the simplex algorithm and this is, Danzig in 47 solves LP. Again, not in polynomial time, unfortunately. So the worst case is exponential, but it's very efficient in practice. Have any of you heard of this package called Cplex? Yeah, so Cplex, I mean, it does lots of things, but it also implements a simplex algorithm. It's a common optimization package. So one can actually cast maxflow as a linear program and then solve the LP, which is an alternate way of doing it. The simplex algorithm also, okay, it's not exactly like Ford-Fulkerson, but it also has this notion of being quote-unquote greedy, which is it sort of moves in the direction of the gradient, which is you look at your objective and you keep trying to improve the objective. And you do it in some consistent way so that finally when you end, you know that there's some termination condition. It turns out that LP is actually in P. There are polynomial time algorithms. And there's a long history of polynomial time algorithms, but in practice, people still use the simplex algorithm. Because even though it is worst case exponential, there is some theory that explains why it runs well in practice. And so max flow, again, if you think about, and if you step back, min cut, which is this discrete problem, can be cast as max flow, and max flow can be cast as an LP, and you can solve the LP. So if you remember our discussion of NP completeness, how we kind of said you can express in terms of Boolean equations. There are many problems that you can express in terms of linear inequalities. So this is called an LP. And sometimes what people will solve is something called an ILP, which is an integer linear program, where maybe now you want xi's to be in 0 and 1. Like maybe you want them to be integers. In this case, the ILPs are actually NP, this is actually NP, well, I'll say NP complete or hard, depending on how you formalize it. So if you force variables to be integers, even with linear constraints, then essentially you can model 3-sat. If you think about what 3-sat is doing and you write things down, you can kind of do a reduction. So integer linear programs are hard, but LPs, linear programs, can be solved in polynomial time. They can be solved very well in practice. And this is an important algorithm that I unfortunately will not talk about. Like I actually was thinking about talking about the simplex algorithm. It is a very important, it's a very important algorithm, both sort of historically, mathematically, and in terms of its impact. Although, I guess it just doesn't fit into this course, unfortunately. So I will end the lecture with that. My main point for today was so that you understand max flow and min cut, this sort of relationship between cuts and flows, and just to know what an LP is. It's important that you at least, hopefully you'll remember the simplex algorithm and you'll remember what an LP is. For many people who actually do research work in any kind of optimization, you will bump into an LP or an ILP at some point and then throw it to a solver. And so this is a very common way of representing problems in such a way that they can be directly solved. Okay, so all right, I will end the lecture and take any questions that you have. Any questions from the remote audience? All right, if not.
Polynomial time algorithm. Like, how do the polynomial time algorithms for max flow? I guess you can just use your own polynomial time algorithms for LP.
Oh, actually, there's the simplest algorithm is the Edmonds-Karp algorithm. So the Edmonds-Karp algorithm simply says that if, when you're doing Ford-Fulkerson, if you do BFS, if you actually just do what I wrote, which is do BFS and find the shortest path in terms of the graphs, then it converges in polynomial time. The proof of that is quite non-trivial. I mean, it's not that nice. It can be done in like half a lecture. But it just says that if you use BFS at each step, then you will terminate in something like, mn squared or maybe something like that. No, actually, you probably would not use the polynomial time algorithms for LPs are quite complicated.